Hi, Chinthaka.
Boby, hello.
So we are back to the class.
Back to the class.
Hey, what is this? We have discussed something last class.
Remember we talked about the lids, right?
Ah,
If it
okay.
would add some resistance to
Also, this
measuring
RX is the one we want to measure, but then there are some lead wire resistors which was troubling for.
Yes.
Or then there was a method to solve that.
Exactly.
Got it.
You know, when you were doing this circuit, I was thinking, you know how we did a full bridge, push full manner, and we also did
the bridge circuit. Correct.
bridge, and also
yeah, we discussed the quarter bridge and full bridge.
Full bridge, right?
There is also half bridge which we did not discuss.
Yes.
Yeah, but probably students can check that.
Yeah. Calculations would be similar.
Correct.
The technique will be.
Yes.
So for this particular situation,
do
you think you can use a bridge?
Oh, so you mean if I use a bridge, will this problem be solved or not?
Yes.
That's the question.
Yes. I mean, what you just did was,
with just RX. But if it's a bridge,
let's say it's all 4 channel, for example, then how would that work?
Maybe we have to draw and check. It may not be obvious. Right. So the quarter bridge is, I think, what we discuss. So there were 4 resistors. This was the RX, which we wrote it as R naught into 1 plus or minus Kx. Everything else we said matched to R naught.
Yes.
Which is the nominal resistance. Yes. And then this was connected to Vs.
Supply voltage.
Yeah. The excitation voltage.
Sorry.
And then we took output from here. So your question is, okay, so the bridge itself is far from the measurement unit.
Yes.
Yes. So I have the measurement unit here, and the bridge is somewhere here. I'm not drawing the full bridge. It's something like this. So that means I have excitation, it has to reach here.
Yes.
Then the ground has to reach here. Then the output will be connecting back to this.
Correct.
Okay. So this means again, there will be lead wires for lead wire resistance. Correct? Yeah. So one thing is, suppose if we can maybe use some, so see, so far we were using,
Yeah, you had your supply voltage, excitation voltage, and another voltmeter to measure.
Correct. That's what we have shown here.
Yes.
So actually, I had some problem there itself. But see, I connected the voltmeter here.
Yes.
And then I remember the V naught for this. I think V naught was, output voltage was some Vs excitation voltage into plus or minus Kx divided by, for quarter bridge it was Vs by 4 into 1 plus or minus Kx by 2. It was something like that. So let's say for a certain Kx, I am expecting, let's say, 10 millivolt. Okay. But when I actually measured, I got much lower than that.
Much lower?
Yeah. I don't know.
Why is that?
So there itself I have a problem. Then comes the lead resistance. Correct?
You might not get.
Yeah, I should be able to measure at the, if I'm measuring close, not from far distance, I should be able to measure that correctly. Then I would like to solve this problem.
Yes. So you're saying that problem will get worse if you're far away. If
Could-
it's
could be.
bad when it's close,
Yeah.
it's probably worse.
Yeah.
It's far away.
Yeah, at least I should be able to measure from, directly from the bridge.
Yes.
First, I will reach there. Then we will go for.
Okay.
So, I was thinking, what is wrong? In the sense, this equation we derived for open circuit voltage. Bridge was open, and then the Rx changed due to the strain or due to the temperature or due to some parameter. I was expecting, let's say, X millivolt. I got maybe 0.8 X millivolt.
80%.
Yeah.
So the only thing I can think of is there is something else that's drawing a voltage. And if that's the case, there must be some sort of resistance. Which means what you're measuring.
Or what you're trying to say is we have derived it for open circuit. It may not be open circuit now.
Yeah.
Because we have connected something across these terminals. Probably it is drawing some current.
That's right. Which means there's some motive.
Yeah. So there is some current, and then no more these equations are valid completely. Partially it is valid, right? I think we discussed this earlier, some kind of loading.
Yes.
We said our measurement system should not load the measurement. Now, in this case, this voltmeter or the meter that we are using must be loading the bridge.
Right. So, what do we know about this voltmeter that we are using?
I know the conventional voltmeter where, there is no one may be using these days. There is an electromagnetic system and a pointer.
The one that yeah.
Correct.
Okay.
Correct. It's an electromechanical system. There, essentially, the work it is doing or the energy for it to display has to come from the measurement.
So it's drawing some.
Definitely, it will be drawing some current here. So that will not be negligible.
Yes. So you need to consider that.
Yeah. So that may not be an option. So we will need some instrument that gives very high input impedance. So, which means probably we will have to use what?
What about these new voltmeters that we use? Are they better than the old ones?
You mean this multimeter?
Sorry.
Yeah. So they are actually battery powered, as you can see. So that means there is some electronics inside,
right,
to kind of ensure that
it doesn't drop down.
Yeah, the input impedance is high. Depends on the make and its specifications, but it's possible.
But then if your sensor is small, you're introducing a very large height of current measurement instrument.
Correct.
So you're asking, can we use something else?
Yeah.
At the circuit level.
Yeah.
To get rid of this problem.
Because this course is also electronic system related course. So can we use some electronics to get some output voltage and provide? Well, actually, what I need is some instrument that can give an output voltage, but its input impedance should be very large. So let's say if these are A and B, I can connect it to them. It should not draw any current. Approximately zero current. Then I'm good.
So inside this box,
I don't know what it should be,
but something high.
Something high. So probably some electronics we have to use. What I think some of the previous courses they might have studied. Using operation amplifiers.
Oh yes. 1/4 operation.
Yeah.
Yeah, no, only have pipe.
Correct.
And you can amplify your signal too.
Correct.
So
That could be an option. Maybe we can think about, there are some basic building blocks for using op-amp circuits. With that, can we realize? Maybe we can check that.
Okay.
So maybe suddenly that strikes our mind, maybe just an inverting amplifier. I'm not sure whether it will help, but we can try out. So inverting amplifier, this I am sure they might have studied. So let's say R2 is in the feedback and R1 is the input resistance. So if let's say V in is the input, you have a current of V in by R1 going into this, that flows through this, and you get an output which is minus V in into R2 by R1. This we know, but I don't know whether I can use this because this one, if you look, it is drawing some current from the source.
see in that resistor.
Yes, because there is V in by R1 current. So the moment I put, let's say 10K, input impedance is 10K. Right. So I will be drawing some current from here. Not be good, not the best. The other one, what we know is maybe the non-inverting amplifier, where the configuration is almost the same. Only thing is, we are giving the input to this terminal, Vi. So where it's going to the input of an op-amp, input terminal of an op-amp, non-inverting terminal, doesn't theoretically draw no current. So that means the current drawn from the source will be negligible. It will not be there theoretically. So for this configuration, we know the output voltage is V in into 1 plus R2 by R1. Because this is at Vi, there will be a current of Vi by R1 here. The same current flows through this. So the output voltage here will be dropped across this plus Vi. So this is, so here advantage is it will not drop current. So input impedance is very high and you have some amplification also. But only thing is I can connect to either A or B.
No, that's kind of draw.
Yes, no, not both. So I may have to use two of this amplified, measure both, and then subtract. Looks yeah, looks very so
very elegant.
Correct. Also, I may be measuring two quantities of almost equal, near values and then subtracting them. That's not the best idea. So if we can somehow get an output voltage directly proportional to the difference between the voltage between the terminals A and B, that will be nice. Not sure how to do. So only thing what I know is here we can write it as V into R1 plus R2 by R1, and here it is minus V into R2 by R1. So this configuration gives something negative, this configuration gives something positive. This much we know, but the gain is different. So somehow if you can combine these two, probably we can.
But not in the sense of combining.
Because
you said that's not a very good solution.
Yeah.
But even combining the idea.
Combining the idea. So maybe we can try this. Let's take this inverting configuration, which is this. let's say this is a VB, some voltage, R2, R1. If this is grounded, we know the output, which is VB into minus R2 by R. Sorry. Now, this terminal, instead of grounding, suppose if I give VI or if I give VA.
VA in this.
I mean, this we give VB. No? Let's say we give another voltage VA instead of grounding. Then I'm going to get some output due to VA also. Yes, correct. Like this. Yes. So I'm going to get plus VA into R1 plus R2 by R1.
Mm-hmm.
So I'm not getting something nice.
Yeah.
I mean, one thing is negative, good. See, what I would like to get is maybe VM minus VB into minus R2 by R1. Then it will be good. Right.
But you're here considering them as separate outputs, right?
So yeah. So maybe it is
Ground
not
and then
correct. Maybe it is not obvious to the students. Correct. So I'm applying superposition. So let's say if VB is 0, this voltage is 0. So we are applying superposition. Let's say VA alone is applied. Then I will connect this to ground case. Or VB is 0 at that time. Then I have this output. Next time we will apply VB alone. This will be at ground. So I have VB into minus R2 by R1. So let's say this is TA. Now, if I want to make this VA minus VB into R2 by R1, that means I have to somehow cancel this and bring R2 there. Suppose if I can cancel this and replace this with R2.
then you have, okay.
VA into R2 by R1 minus VB into R2.
Then you have a nice gain plus the
difference.
Right? That's what you're.
Yeah. So that means this VA, I will have to do something here. Let's say that VA was, I'm going to give only fraction of VA. Let's say VA into, I want R2 in the numerator, no?
Yeah.
So I'll write R2 there. I want to cancel this R1 plus R2. This is what we want. Now, how to get this? Suppose from VA, I can get this voltage. That can be given to this terminal.
What?
Yeah, it's just a voltage divider. So if I do, let's say, 2 resistors like this, and if VA is here, this voltage is what I wrote here. VA into R2 by R1 plus R2. So then these two are getting cancelled. We are getting the final output V naught equal to VA minus VB into R2 by R. So we have a nice output with a gain of R2 by R1. It's giving the difference in output. Still, I don't know whether our problem is solved.
Because we still have resistance.
Yes, we still have. I mean, the moment I connect this to some terminal VB, it's going to draw some current.
I want to draw some current.
Same here. So if I connect this to the bridge, still there is a problem. It just amplifies the difference and gives you.
I mean, your initial problem of having a small voltage and now amplified.
Yeah.
But
Yeah.
the problem remains.
The problem is still there. So this means somehow we need to provide high. In this A and B, I should not connect directly. Something should be there in between that provides very high input impedance. So I think this also students have studied something called this voltage follower.
Yeah.
So maybe that can be used. So let's say this is what we discussed. Now these terminals, I mean voltage follower, just to refresh. It's a unity follower, or the output is fed back to the input directly with no reduction in the output voltage. And this is Vin or Vi. So if this is Vi, this terminal is also Vi. This V naught is equal to Vi. So whatever we give here is available here if it's within the range of the op-amp. And because this is going to the non-inverting terminal of the op-amp, the current drawn is negligible. So it provides high input impedance. Okay. So we could use two of this in front of this.
But we have used two because you have
We'll have
A
used
and
two.
VB.
Yeah. So we will have to use two of them. So that could be one solution. So I'll give this. Maybe this is V2. Let's say V1. I'm using different. I mean, here we use VA, VB. Here it is V1, V2. Otherwise, it may get confused. So if we do this, I mean, this is a voltage follower. So V2 is available here, and V1 is available here. Okay. So let's say V2 is the voltage at
EA.
Yeah, VA or VB. VB, for example, and let's say V1 is the voltage at V, capital A. Okay. So this will not draw any current. So the actual problem that we were facing, because we have drawn from current from the some current from the output of the bridge. There was a loading, and then these equations were no more fully valid. So there was error. Now this problem is not. And then whatever you get here will get amplified by R2 by R1.
So there are basically, there's no current drop because both amplifiers will have high input impedance.
Yes.
Then you now get the signal even though
And give it to
less it is. So even if there's a drop,
yes.
it will be amplified.
Yes. Okay. So this is one option. Now,
but I feel that you don't like this.
Yeah, I'm not fully happy.
Yeah.
Because I can see that something more can be done without much effort, right? Because let's say if I want to change gain, now I have to change both R2s.
Yes.
I'm not that happy with that. I would like to change just one resistor and change the gain.
You're getting green now.
Yeah. So, I mean, this idea is good, but not good enough. And before that, actually, I wanted to bring in one more point. This unit, let's say I connect these two and then give same voltage. Not for the bridge. Not for the bridge. I just connected these two. And let's say I connected to some voltage source. Maybe I'll call it as VCM. Some voltage, right? What will be my output? It was VA minus VB.
In this amplifier, yes.
So, the voltage output will be 0.
Not true. If
Correct.
we're giving the same voltage.
Yes. But these two terminals can be at some voltage. In the sense, it can be both at 2 volts, but your output voltage is 0, theoretically. Right? If there is some mismatch for this resistors, it will not be valid. But if you have matched resistors, this is possible. Why I brought in this is, if you look at bridge, let's say Kx is 0.
No.
At the time,
0.
When Kx is 0, you have difference in voltage or V0, which is 0. But this terminal has got Vs by 2 volt.
If you measure
separately. This terminal also has got Vs by 2.
Yeah.
So, there is some voltage which is already there and you want to measure that difference alone. Correct? So, what it says is, signal which is common to these terminals, it's able to reject.
Okay.
Correct? Yeah. So, that's an additional benefit it has. All circuits will not have this property. So, it's why I mentioned VCM is the common mode voltage. A voltage common to these two modes.
They equal.
Yes. Now, they need not be equal. I mean, I can have the voltage that we are interested to measure. Let's say, maybe I call it as VD. This is what we are interested to measure. But VD may be riding on this common mode voltage.
On top of that.
On top of that. Or even to make it more clear, this can be some, let's say, V2, and this can be V1. Let's say 2.51 and 2.49. So, you have very small difference in voltage, but you have 2.5 volt common mode voltage. Okay, right? So, that common mode voltage, VCM, is defined as V1 plus V2 by 2. Right? So, the point is, this difference circuit, right, or the difference amplifier is able to provide an output that is proportional to the difference alone, and it's able to reject the common mode signal. So, I think if they refer, we can see some performance factor called CMRR, common mode rejection ratio, which is the ratio of difference in gain by common mode gain. AC. AC is the common mode gain, AD is the difference gain. So, ideally, we want no gain for the common mode signal and we want large AD. So, usually this value will be very large. So, usually it's also expressed in dB. Now, why I brought in this is, this configuration has this benefit. Okay. Provided all these resistors are matched. If there is a mismatch, there is a problem.
So, what you're saying is,
Yeah.
you can take the two arms of the bridge circuit output separate and connect them to these two. Is that what you're trying to say?
No.
Yeah.
I can do that, then there will be loading.
Yes. Which is, we talked about the difference.
Yes.
So, then what are you trying to get at?
So, what I'm trying to say is, I want to use this property, the common mode rejection property of the circuit, right, For that, I will make all these resistors of same value.
Okay.
So the common mode rejection is perfect.
Uh-huh.
Let's say I make, when an IC is made, all 4 resistors are made using same process. So the variation will be very small, right? So I get matched resistor, right? Or resistors. So then I get very good CMR. I'll use that. Then for amplification, like I said earlier, I would like to just change one resistor alone, not all. So we have drawn some voltage follower circuit here that we will replace with or modify with some scheme that can provide a gain control. So let's try.
So you're not depending on the gain from these resistors?
Yes.
Anything else?
Yes. So let's say, we are going to just modify this buffer circuit that we have drawn. So let's say in the buffer or the voltage follower, I introduced a resistor here in the feedback. No effect. Because anyway, there is no current through that. I will do the same for the top also. Same thing. So I have V1 and V2 here. This terminal I will get V1, sorry, V2. This terminal I will get V1. Let's say these are also made of the same R. Okay. Now we'll do some small modification. So this terminal has got V2 volt because if this is at V2, this will also be at V2. Follows that volt. This terminal is at V1. Now let's say if I connect a resistor here between this V2 and V1, we'll call it as maybe RG. So that means there will be some current through this, which is V2 minus V1 by RG. This current cannot come from here, cannot come from the input of the op-amp, no? So it will be coming from the output of the op-amp. That means this will be making a drop of that current into R
That you place
across that resistor. And this current cannot enter this way. So it will be flowing in this way. So this will be making a voltage drop here. Now we can look what is the actual voltage available here and here. So we said this is V2. So V2 plus this drop will be this voltage. So this will be V2 plus V2 minus V1 by RG. That's the current into R. That is the voltage here. And the voltage here will be, this is V1, so this is V1. So it's V1 minus drop here, correct? So V1 minus, the current is V2 minus V1 by RG. Into R. Now suppose I give this to this and this to this. This unit is going to find what's the difference between these two. Or it was VA minus VB.
differential.
Yes. So that means whatever this voltage minus this voltage. So that will be V1 minus V2, the first two terms. Then I can write it as, minus of V2 minus V1 means V1 minus V2. So, V1 minus V2 into R by Rg minus of V1. So, 2 times this term comes. So, this will be 2R by Rg. Or the V0 here is equal to V1 minus V2 into 1 plus 2R by Rg. Right. So, now if you look, these are the 2 voltages that we have. We want to measure the difference of that. We have that here, V1 minus V2, multiplied by a gain factor of 1 plus 2R by R. Now, I can choose to vary this Rg if I want a different gain. I don't need to change all the R's, right? Correct? So, that's the reason, in fact, this Rg is kept in the drawing bit outside. So, in the sense, if let's say this is available as an IC, we will be getting only these 2 terminals, V2 and V1. And then there will be 2 other terminals to connect the Rg that you want.
The standing ICs, right?
Yes, yes.
That's what you know.
Yes. So, this amplifier has got some nice name, you know it. Once you have this full configuration, it's getting the difference output, providing very high input impedance, and it has got very good common mode rejection, right? All these features are there. This amplifier is called instrumentation.
Okay. She's using so many.
Yes. So, the short form is INA. So, when we show just a block like this and Rg and the 2 terminals here, it shows it's an INA with a,
and that's what's inside.
Yes. What is inside is these 3 op-amps. And we have this, I'm not trying to sell product, but let's say INA, maybe if a student search, there is INA 127 or 101 and so on. Is there in an IC form where all these resistors are inside. They are factory trimmed, so that is as matched as possible. And then these 2 terminals are available so that you can connect your RB and play with it. Whatever gain that you want, using this equation, you can set and get the gain.
Okay. But in this instrumentation amplifiers, so what's the RG? Is it connected to some potentiometer or something?
If you want a variable one, it can be a potentiometer.
It's normally like 10, 100.
Yeah, so you can decide. Let's say you want a gain of 100. Then you look at what is the value of R it is used, and then accordingly calculate RG. Right. So now this we can use instead of this meter that we are showing.
So basically what you're saying is you can go out and buy this amplifier connected there.
Yes. Then this problem is solved. Right. So now we will not have the loading problem. It's not because it's no more going to draw current from these terminals. So you have very high input impedance, Similarly, I mean, we were saying this has got Vs by 2 common mode voltage. Because it's, in fact, students can also check for, let's say for this IC, what's the CMRR? Sorry. It's available. I think it's in the range of 100 to 120 dB. Means 20 log AD by AC. Right. So common mode rejection is very good. You have very high input impedance. That is all required for this application.